Hi everyone, in this video we're going to talk about properties of periodic table. Let's start. Okay, this is the latest periodic table. Let's start with the special names of the groups. But first let's talk about these group numbers written on every group here. For example, this is written 1 here, this is written 2 here. In fact, mostly you have seen that this is 1A, this is 2A, then comes 3B, remember? Then 4B, 5B, 6B, 7B. Then you have 3 8B groups. Then you turn back to 1B and 2B. When you are finished with these transition metals, you pass to 3A, 4A, 5A, 6A, 7A, and 8A. Now, in modern periodic table, we mostly use these nomenclature as numbers. For example, the third group represents 3B, but the 13th group represents the 3A group. Okay, now we can just tell their special names. 1A is known as alkali metal, and 2A is known as earth alkaline metal. These red ones in the middle, they are transition elements. They are all metals. 3A is known as earth metal. And 4A, 5A, and 6A, they have no special name, but because that the 14th group starts with the carbon, it's known as the carbon group, and next one is the nitrogen group, and next one is the oxygen group. And here is we have 17th, 7A, they are known as the halogens. And 18th group, of course, they are known as noble, in other words, inert gases. Now, what about the ones found in below here? They are inner transition elements. Now, why do we call them inner? Because they're just coming the inner side of these transition metals here. Just look at these. Between the atomic numbers 57 and 71, these one, the pale pink ones, are known as actinides. Not actinides, sorry, they are known as lanthanides. And this one, the green ones, are known as actinides. And these pink ones, here is bore, silicium, germanium, arsenic, or antimony, they are metalloids. In other words, semi-metals. Physically, they look like metals, but chemically, they show the properties of non-metals. La 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 la. Okay, now comes the periodic trends. We are going to talk about atomic volume, atomic radius, just same first ionization energy, electron affinity. But we're going to start with the easiest ones, atomic number and mass number, these ones. Now, these ones increase when you go both sides. When you go along a group from top to the bottom or left to right, they are increased, atomic number and mass number. Now, all the other properties, electron affinity, or we're going to talk about metallic properties, if they increase one side, they are going to be decreased on other side. Atomic radius increases when you go along a group, because the first period includes one orbit here, the second period includes 2 orbit, and it goes like this, so the atom just gets fat and fat. But when you go along a period, in this case, number of valence electrons increase. So interaction force between the proton and those valence electrons increase also, just the atomic radius gets smaller, and atom also gets smaller. And what about first ionization energy? As we have said already, when you go along a group, atomic radius increases. So this means that you need just less amount of energy in order to get one electron from the atom. So when you go along a group, first ionization energy decreases. And when you go along a period, because the atomic volume is decreased, then you need to have more energy to remove one electron from the atom. And what about electron affinity? Electron affinity is similar with the nonmetallic property. So this is the tendency to gain an electron. So it is all about the nonmetallic properties for a nonmetal to become an anion. So when you go along a group, this is going to be decreased. When you go along a period, when you go along the nonmetals, this is going to be increased. Electronegativity. Now we're going to talk on about electronegativity in later slides in detail, but it is again similar as electron affinity and nonmetallic property. When you go along a group, it is going to be decreased. When you go along a period, again to the nonmetals, it is going to be increased. Electron giving tendency and metallic properties are just the same. If an atom has a really high electron giving tendency, this means that it has high metallic property. So it is going to be increased when you go along a group and decrease when you go along a periods. And comes to nonmetallic property. Nonmetallic property is just same as electronegativity and electron affinity. It is going to be decrease when you go along a group and increase when you go along a period. And comes the basic property of oxide in aqueous solution. Now let me show you with a reaction. For example, if you have sodium oxide and when you add it to water, it produces sodium hydroxide. This means that metallic oxides show basic property when you dissolve them in water. So it is just the same as this metallic property here. We can equalize them. So this is going to be increase when you go along a group and decrease when you go along a period. Now comes the acidic property. Acidic property is just same as a nonmetallic property. For example, if you have sulfur trioxide gas, when you dissolve it in water, you produce the oil of vitriol, hydrogen sulfate. So this means that nonmetal oxides show acidic property. So they are going to be the same as this nonmetallic property here, and decrease when you go along a group and be increased when you go along a period. Now here are the types of the atomic radius. For example, the covalent radius. If we are talking about the covalent radius, this means that the covalent bonding here, like in fluorine, F2 here, and like in chlorine, 2 here. So the distance between these two nuclei is known as the atomic radius. So what about the van der Waals radius? We mostly use this term to identification of radius of noble gases, on like here neon here, or like here argon here. We're talking about their solid form here. So this is neon, and the distance between two nuclei again gives you the radius here, and distance between the two nuclei gives you the radius of this argon atom. Now for ionic radius, this is a little bit different than the other ones, because if you're talking about the ionic radius, this means that for metals, you're talking about cation radius. For nonmetals, you're talking about the anion radius. So when an atom gains an electron, this means that its radius is increased. When loses an electron, its radius is going to be a decrease. That's why they have really difference between their quantitative values of their radius here, sodium and fluorine. Now comes the ionization energy. This is the amount of energy needed to remove an electron from an atom. And if we just label as a reaction, we are going to label as an endothermic reaction. First, when the ionization energy is measured, we use the atoms or the ions in gas phase. This is important. So if you just like to remove one electron from a neutral X gas atom, this is known as first ionization energy. And this is shown with IE1 here. So let's say that you have the plus 1x and you like to remove one more electron. let's talk about the elements in the second period and their first ionization energy trends. In the second period, we have lithium, beryllium, bore, carbon, nitrogen, oxygen, fluorine, and neon. These are the second period elements. Now remember, ionization energy increases this side when you go from left to the right. So this means that neon seems to have the highest ionization energy, where the lithium seems to have the lowest ionization energy. So you can really just order them like this. But in fact, this is not the true order. There's an exception here. Beryllium and bore here, and nitrogen and oxygen here should just change the places, and the real order should be like lithium is smaller than bore, then comes the beryllium, then comes carbon atom, then comes oxygen, then comes nitrogen, then comes fluorine, and finally, yes, we have the highest ionization energy for neon. Now the reason is spherical symmetry that is shown by the groups 2A and 5A. Now remember, symmetry gives an atom a little bit stability, not as much as the noble gases, but really high stability. So this means that you need more energy to remove an electron from them. So when you just order the elements in the same period according to the ionization energies, please be careful with the changing places of 2A and 3A and 5A and 6A. So what about their graphics? Let's say that this is ionization energy 1 here, and this is atomic numbers of the groups of the elements in the second period. 3 here, 4, 5, 6, 7, 8, 9, and 10. So this is 1A in fact. Let me write their group numbers also. 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A. Let's start drawing the graphic. Now let's say that this is 1A, its ionization energy. Now 2A will really be high because 3A is going to be between them. Now 4A just gets higher, and 5A is going to be really high because you're going to put 6A's ionization energy between the 4A and 5A. Now 7A, you're just getting closer to 8A. Noble gases is going to be high, and 8A is going to be the highest. So please just combine all these dots here. You're going to have a graphics with 3 peaks here. So these 3 peaks represent the groups with the spherical symmetry: 2A, 5A, and 6A. So if you just like to draw the ionization energy of the 1A group, but in the next period with the atomic number of 11, what would it look like? So when you go along a group, the ionization energy decreases. So if you just like to continue this graphic, it's going to go really downwards here, lower ionization energy than this first one. Now comes electron affinity. It is the amount of heat change when an atom or an ion gains an electron. Now please examine these examples. You have fluorine gaining 1 electron, and it is written as plus 328. If this is written on the product side, this means that you have an exothermic reaction. That's why this is shown with a minus sign. So representing exothermic reaction. So these above reactions exothermic, but this does not mean that all the electron affinity values will have negative sign. For example, just examine these following ones. Beryllium gains an electron. In this case, it needs energy to gain an electron. So this is electron affinity with a sign of plus here, plus 240 kilojoules. And magnesium, this is a really good metal, so it doesn't want to gain an electron. So if you like to give an electron to it, you have to give heat also. So this has an electron affinity value again plus 230 kilojoules. And neon, this is a noble gas. It really have small tendency to gain electron. It needs 29 kilojoules to gain that electron. Electronegativity, it shows the tendency of an atom to pull the bonds that make up the bond. In order to define electronegativity, Pauli scale is used, and the highest electronegativity value is 4.0, and which belongs to fluorine atom. Now I have to tell an exception here. If we are talking about the highest electronegative atom, you're going to tell me that this is fluorine. But if you are talking about the element with the highest electron affinity value, you should tell me that is chlorine. Just please be careful with this exception here. Acidic and alkali properties of the oxides. Some of the aqueous solution of the metal oxides show basic property. So these are known as basic oxides or basic anhydrides. Now look at the examples. Sodium oxide is dissolved in water. It produces 2 sodium hydroxide. So dissolving sodium oxide in water is not in fact a physical change, but it is a chemical reaction. So dissolving process mostly means physical changes, but in this case it has a chemical meaning. Potassium oxide, you put it in water, it produces 2 potassium hydroxide. Calcium oxide, you dissolve in water, again a chemical reaction, it produces slaked lime, calcium hydroxide, and a strong base. Barium hydroxide, this is just same as the calcium oxide, it produces barium hydroxide, again a strong base. And some of the aqueous solution of the nonmetal oxides shows, in this case, acidic property. Remember, we talked about their trends before. These oxides are called as acidic oxides or acidic anhydrides. For example, carbon dioxide gas dissolving in water, it produces the carbonic acid, a weak acid. Or sulfur trioxide gas, it reacts with the water, it produces hydrogen sulfate, oil of vitriol, which is a strong acid. And dinitrogen pentoxide, when you put it in water, it produces 2 hydrogen nitrate, again a strong acid. Now finally, we have the summary of periodic trends in this picture. Now you see here is the atomic radius, here and atomic radius here. It increases when you go this way. So these are the periods here, and these are the groups here. So metallic property increases this way here, because you have the highest volume of the metals here. So if you have a high volume, this means that it is going to give its electron easily. You have the non-metallic character here when you go to the non-metals, but be careful, these are the noble gases. We don't usually talk about their non-metallic character, but till the 7A you can talk about the non-metallic character. Electron affinity here and ionization energy here. Ionization energy will be highest for helium because it is a really stable noble gas and it has a smallest volume, so you need a high amount of energy to remove an electron from it. Electron affinity increases when you go this way, but remember, electron affinity has the highest value for chlorine, but electronegativity has the highest value for fluorine atom. And again, ionization energy just increases this way when the number of valence electrons increases along a period. So you can tell that this is the summary of what we have done so far.